Uh, okay, welcome back. Let's start. And so I have to do the usual stuff. Just please interrupt me. And so let me just remind you what we had before. So for any small category C, we saw that set to the C is a topos, right? And uh, then I said that I don't like this construction. Something is missing. It's not generalized enough. And then I said that I want to provide three reasons for that. So we saw somehow the logical one. So it was something like that in any topos E and any object X, say, then the lattice of all subobjects is a Heyting algebra. So I didn't prove that, of course, but I claim that. And then something even more, but then the whole thing is that you have intuitionistic logic available because you have Heyting structure in all subobjects. And so that's good. But at the same time, you don't have the classical logic all the time. Sometimes you have, like in these toposes, but it is not always classical, right? And then the problem, the logical problem is that so far I have no machinery to produce, say, classical, or the real term is Boolean toposes. So if you like to apply it to classical setting, you don't have it, right? Yes, you have these guys, but it's not enough. So formally, it means that all the subobjects are not just Heyting algebras, but Boolean algebras. But informally, you can think that you can, have all the classical logic, say, instead of just intuitionistic.
Maybe for this being a Heyting algebra, what is the structure?
So you have, say, disjunction, conjunction, and implication. But the implication is Heyting implication.
Okay, but there's some particular way of defining these in the
So because you have the structure of a topos, always you have these structures here. But the thing is that I have to prove that you have it. And in each specific topos, you can describe it somehow, right? So,
okay.
But anyway, I don't have anything to say today about this thing, except that it is just the first problem that we have. No machine for classicals. Then I said that there are two others, the geometric one and the algebraic one, and then I said nothing about them. Right one. And to explain these two, we had to go through some sort of interpretation of this topos or this category. So, right. So I said, if you remember, that we can read this guy as the category of sets variable over C, and C is my category of what? And then also you can read this in some way, and then we saw that you can read C first. So if this is C, and these are just objects in C, right, whatever, and some morphisms between them. So you read them as simple objects, right, with simple morphisms. And then you read set any object here, which is simply just a functor like this. You read this F as some sort of generalized space, meaning that you have something like this curvy thing, and this is some sort of generalized object. And then F encodes, so what is F of A for any object A here? It is just the set, as you can see here, of all in quotation maps from the simple object A into the complex object X, right? So that was our interpretation. So okay, so I have to explain this more. So what's more? Let's think like this. So example, let's say that I have a set, two sets, X, Y. These are just sets, right? And my C is just what? The power set of X. So all the subsets as a poset, it's a category. And then pick this F from C opposite the set. It reads some subset here, say U, and then you have all functions from U to this Y, the second guy, right? So, and if U is subset of V, then I have to say what happened. There should be a map, say, because it is opposite from F of V to F of U, and meaning that it reads some F over V, right? And then you have to compute something like F over U. So that map is just simply restriction, right? So you read something and you restrict it to V. So it is like F goes to F restriction to V. Right, this is my function. Okay. I have one set, all of its subsets. These are simple objects of mine, right? And then I have some other set. And then I define a functor that reads in U and returns all the functions with Y as a value, but over U. And then the natural thing is just if you go from U to V, actually opposite, then you restrict. So what I'm saying simply is this, that your C, this is your C, and then these simple things are just subsets. These are subsets of X, and you have some Y. This is your weird space, right? And what I'm saying simply is that define F such that it reads one thing like this, and then it stores all the pictures of this Y everywhere, right? Like of this guy everywhere, so like this. Huh? All the shapes of this form inside Y. This is just all the local data of this form inside Y. And since you have all the forms, F encodes all the local data of some form inside Y. Mhm.
Example starts with X, Y sets.
Sets.
You need real set or you need categories?
No, just real simple sets. Yes.
F on the third line, it makes C opposite to set,
Yes.
which means the category of sets.
Yes. Yes.
And so it's a functor.
It's a functor.
And the below is
This is the definition of the functor.
Just define this factor.
Yes, I just define the functor and that's it, right? But then I want to say that, okay, this functor actually encodes what? Encodes all possible local means subset of X, local forms inside Y. And then somehow I'm encoding Y via the lenses in X as a function.
So say F is kind of local description of Y
Yes. According to X.
into it.
Yes. Is it just okay? Right?
I think
No.
this is just the definition.
Yes. So far I did just nothing, right? So I assigned to it's fixed X. Let's say X is fixed forever, and then for any Y I assign the functor F from C opposite to set, encoding the whole data of the set Y as a function, right? So what I'm saying next, okay, so first maybe I have to say that there are many versions of this, right? So you can change anything. You can change like X could be what? So these two can be just topological spaces, not just sets, right? And this C can be just opens of X, not just all subsets, right? And then F with the same definition, but these Fs could be just continuous maps. A restriction of a continuous is continuous, so, right? And you can change it, accordingly, right? You can say that, I don't know, pick Y as some differentiable manifold and X is just R, and these are just open subsets of R, and then here record not all functions, not all continuous functions, but all differentiable functions, and many other settings, right? It depends what you pick as your local data, so you can change it from all subsets to open subsets to whatever subsets, bounded subsets, anything. And then also the other thing is that what kind of maps you want to consider, right? Continuous, differentiable, whatever. And of course, it depends on your setting. You want to capture Y as a set or as a topological space or as a differentiable manifold or whatever, right? So then you add more structure here.
Can you read out the last 3 lines? So before the previous line is
Mhm.
find the objects in your.
Yes.
That's the object.
Yeah.
The object.
No. So what's a functor? I have to define it over objects and over morphisms, right? So object here in C opposite is a subset. So U is a subset of X. And then I have to define what is f of U, and it should be a set because I'm going there. And this is the set. And then over morphism, there is just one morphism because it's a Pope set. So then I have to define a function from one set to the other. And my function is that pick one function over V and restrict it to U. That's my function.
The opt thing is that pretty line.
Yes. Okay. So there are, my point is that there are many versions of this, of course. Not really, because it is just one example. But the example is meant to say something, and that something is that 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 one functor is actually the different ways looking into one given set Y or one space Y, right? So I can pretend that whenever I have a functor, not just on this category, on any category, and it lands in set, I can always pretend that there is some sort of Y, which is my generalized space, and this F is the set of all maps from the object to that space, right? I can't pretend that there is some sort of y. This is some sort of ideal object. There is no y, right? But I pretend. And this is what I explained here, right? So here I'm saying that you have simply one category C, and you have just a functor and nothing else. And then pretend that there is some sort of y, right? And then F just records all maps, and maps in quotation because there's no map, from that object A into my weird space Y. This is not formal, right? It is my informal thinking. I use it to import my geometric intuition to pure category, right? So, okay, this guy, any F like this has a name. Of course, the name is functor, right?
So now you generalize this, and what is the correspondence? So instead of X in the example, now we have set to the one category?
No, I don't have X anymore because X doesn't matter really, right? What matters is just power set of X,
Yes.
all the subsets. So I have C as all the subsets.
So X could take arbitrary categories,
Yes.
and instead of Y,
There is no Y. This is the whole point, right? I have no Y. I want to pretend that there is a Y such that F can be any functor. The arbitrary functor is actually coming from some Y. Right? That's my pretension. So I was saying that there is a name for that, and the name is functor, but actually there is another name, and it's called a pre-sheaf. So any functor from C opposite to set is called a pre-sheaf, say over C or on C. So it's a functor, but I have just another name for that. And remember that when I say that something is pre-sheaf over C, then it means it's a functor, it's a contravariant functor, right? By definition. So, and the name just simply says that there is something missing, right? It's pre-sheaf. Therefore, there is some sort of sheaf that I'm interested in, right? And this is the thing that I'm saying that it's missing. So, okay, maybe I have to keep these two, why not? Go there. And say two things. One, okay, maybe I have, okay, first, maybe I have to say it now. So there is some sort of easy version of that, right? The propositional, the algebraic version, if you like, and it is 2 to P opposite, right? I'm changing C to a poset and set to 2. Simply, it's just a version that I don't care about the morphisms, but simply the value 0 or 1, right? And there is some sort of, analogy here. So, and that's good to keep in mind. So, yes.
is category of pre-sheaves, or
Yes, it's just a category of pre-sheaves, exactly. And then this guy is what? It is then the poset. It's the poset of what? Of, you tell me. There is one opposite. Yes, but since it is just, I don't care about disjunction, therefore it is just downset. Downsets. So poset of all downsets of P, right? The subsets that are closed downward. There is some sort of correspondence between these two, and it helps to see the picture, and I will use it more and more. So the first thing that I want to say is this. Okay, so I claim that pre-sheaves, the category of all pre-sheaves. So pre-sheaves are just some sort of generalized space. So any simple space should be a generalized space, of course, right? Therefore, there should be a functor from C to set to C opposite, right? I read some simple space, and then I transform it, I read it, I pretend that it is actually a generalized space. No,
This is just transformation.
no, yes, it's just a function from a word to another word, right? So how to do that? So here I have it, right? So there, in that weird definition that I have here, there is a way to come up with this functor. Let's call it y, right? So it says that, okay, let's say that I have an object A here, and then ya is what? Is a functor here, right? So therefore it is from C opposite to set, right? So how to define that? We have a way, right? We say that ya of any B, which is a simple space, it's the set of all maps, you know, blah, blah, all maps from B to the space. And the space Y exists here, actually. You have A. So I have some sort of canonical choice here. So simply all, this time with no quotation, all maps from B to A, of course, in C, because they live in C, right? Simply, I'm saying that I have home C BA. That's my definition. It should be this, right? Okay, fair enough. And
Why?
I'm defining Y. So then on object, on object, I have to define Y, right? I'm defining Y. I'm defining Y. So on objects, I have to define my Y. What is the definition? I'm saying that YA is an object here, right? This is just Y of A. So here. Therefore, it should be a functor. And this is the functor. We saw this guy before. And then on morphisms, I have to define my Y. So let's say that I have F from A to, actually it's cool. Say A1 to A2. And then my YF must go from YA1 as a natural transformation, because we live here, to YA2. And then how to define that? So if it's a natural transformation, I have to define it for any object in a natural way, right? So then for B, so this is my alpha, say. So this is alpha B. It must go from this guy on B, which is just home and BA1. I have to go to home BA2. So I have to define this function. And of course, it is just composition with F. B goes to A1, then compose with F. What else? Huh?
So starting with Y, and then Y sub A, it is what?
It's the okay.
You should find Y.
Yes. So then I have to define y on object A and on morphism F, right?
You denote by y sub A, that's the object.
Yes. This is this. This is this. Right?
Then y sub A, parenthesis B is what is
So
morphism object. That was
so I have to define y of A, right? Y of A, whatever it is here. So therefore, it should be a functor from C opposite to set. So therefore, I have to define a functor now. So I have to define it on objects and on morphisms, but what I'm saying is that it is actually the home functor. So, and on morphism, just composition. Go
It's
on.
just a lot of notation without any words explaining. So in particular, you've got 4 symbols in a diagonal line there.
Mhm.
Is that A equals Y F?
A this guy, right? It's alpha. So what I'm saying simply is that you want to define a natural transformation, and then this is just mathful. So just let's say that's alpha, right? I want to define some natural transformation alpha. And then this means that I have to define my alpha on any B. Yeah. Okay, what I'm saying then, it is kind of too complex. It seems too complex, but it is not really complex. So simply what I'm saying is that this is my C. Yes. So I have to define alpha on any B, right?
That's third notation defining that function.
No. So you have to define natural transformation alpha. This means that you have to define it for any B as a function from this home set to that home set, right? B is some arbitrary object in C.
You're defining alpha.
Yes, and what? Yes, so I have to define alpha B of some G. G is here, right? Which is just go with G, no, with F and with G.
So now you define.
Yes. But what I'm saying, it seems it is just too messy, but it is not that complex, right? So simply I'm saying that here, this is the bigger world of generalized objects. Here you have the simple object. So you have A here, you have Yoneda of A, that's called the Yoneda function. And so how does it work? It simply works like this, that let's say Yoneda A of any B is home B A, right? So I lost. So that's it, right? Just the definition. So what I'm saying simply is that you want some sort of generalized space. You have to define a functor, right? And the functor must map something to some given space, and that given space is A. Right? And then we also saw that this Yoneda is actually an embedding. So meaning that so if I have home A1, A2, then since Y is a functor, right, it maps it to home Yoneda A1, Yoneda A2, right? Because it's a functor. But this Y is a bijection, like between them. Meaning that if I have one map from this A1 to this A2, like F, then I have, of course, because it's a functor, I have a map here, right? But then it is just impossible to map two different maps to one map. It's one-to-one, and it's a bijection. So if I have an abstract transformation, all of them come from one, right? So this guy actually sits here, right? With all the morphisms, with different names, but it is just here. So it's just some part of it, of course, but it sits. So it does not like that you go here and then you just glue some morphisms together. So everything is just intact. And also it is not the case that when you go to the bigger category, you get more morphisms. You have just the same morphisms that you had before. It is just sitting there, right?
This is called the Yoneda functor?
Yes, this Y is Yoneda functor, or of course Yoneda embedding for obvious reasons.
I extract here.
Yes. Well,
You want to start it, so what's
yes.
there?
So the theorem is that Y mapping this set to this set, of course, because as a functor, is a bijection. So you can write like this. That's form A1, A2. But the map also is important, right? So it is okay. So what? Well, it is just too hard. Maybe I should use this. Okay. This is the first thing. So if you find it just complex, it is not complex, but it is messy. So maybe it helps, I'm not sure, but maybe it helps to see the same thing here, right? So here I said that you can go from C via one embedding to set to the C opposite. So here I'm saying that you can go from P to the downsets, right? This is just the same thing. How to go there? So you read some element A and you map it to, what's the canonical downset? Exactly. So the downset generated by A, everything below A, right? So I'm actually doing the same thing there, right? So I'm mapping what? I'm mapping A to Yoneda A, which is just the downset of A, right? Everything below A in some systematic way, okay? And then we know that this is just embedding, meaning that if A is less than B, of course, this guy is less than this. So subset of that. But if you have this subset, then you have this, right? So you don't add any new morphism. Up makes it down, downset. This is the only thing that's important, right? Since I have up here, everything is down.
You need that to preserve the direction.
Yes, exactly. Because I cannot do otherwise. So you have to use your up either here or there, right? So the second thing that I want to say is even worse. So that is the Yoneda lemma. So it simply says that so the form is this: home Yoneda A F in set to C opposite it is just equivalent with f of a, and the map here, the description is something that I will explain. And then it is natural in A and F. Okay, good. Let me first explain what I'm saying really. So this F is some guy in set to the C opposite. Yoneda is also there, right? So this is like, this is Yoneda and F lives here and there are some morphisms, right? So what I'm saying is that if you have a morphism from Yoneda A to F, it is actually equivalent to have one element in F of A. There is a correspondence between them. Okay. And what is the map to do the correspondence? Maybe it's easier to write it this way. So if I have one alpha, say, from Yoneda A to F, how to get some element to inside F of A? No, it's just the definition. I have two things, and I'm defining one map to say that actually that map is an isomorphism, not any map. And what is the map? So you have one alpha from this guy to that guy. How to come up with some element in F of A in a canonical way? Yes. So if alpha is a natural transformation, so it's defined over, for any element. So therefore alpha A, if I use, say, alpha A, then it is from Yoneda AA, which is home AA, to FA. And this guy, there is one canonical element here, identity. So therefore I can apply alpha A on identity A and I get something here. So the map then is that it maps alpha to alpha A of identity A. It's just here, right? And I'm claiming that this map is an isomorphism and natural in A and F. Of course, I won't prove it because it's just a mess, but I will explain what it says because it seems kind of weird. So what it says is not that complex. So it simply say, so we had that weird definition, right? That I said actually, so I keep this. Identity of A as an element here. Yes.
Why did you write it there?
Because I want something here, right? At last. So my point is that this guy lives here. You apply alpha A on it, and you get something in F of A. So therefore, this is the definition, really. I don't get. So alpha sub A is a map here, right? Home AA to FA. Yes. So then one canonical element in home AA is identity of A. Apply alpha A on that identity of A, and then you get some element in F of A. So then I start with alpha and I end up with some element in F of A. That's my definition. So you read alpha, some element in F of A, right? And maybe again it helps to see it for that say propositional version. So what's the corresponding thing here for this guy? It would be what? It would be so for any A, there is some Yoneda, and Yoneda is this, right? In this case. This is Yoneda of A, okay, in some sense. And then this says that all the maps from to some downset, F could be another downset here, any downset, is in correspondence with D of A, meaning that so D of A is either 0 or 1. So what I'm saying simply is that this guy is equivalent to this. Because of course there is just one morphism, right, from anything to this downset. So I'm saying that there is one morphism if and only if this guy is 1. So A is in D if and only if downset of A is a subset of D. And this is true for any D and any A, because D is a downset. But this obvious thing becomes more complex because you have morphisms. The intuition here is this, that I said when you have F as a pre-sheaf, you can read F of A as set of all in quotation maps from A to some space assigned to F, say to F itself, why not, right? So the problem is that, yes, okay, I can read it like this, but then when you go to set to the C opposite, and F leaves there really, and your Yoneda A as a copy of A lives here, then both of them are in one category, then it really means something to say that all maps from A to F. All maps from A to F are these guys, right? That's a formal meaning, that's just some informal thing, right? This guy says that there is some sort of consistency sanity check, that there is a correspondence really between them. So these are the formal maps from A to F. These are just informal maps from A to F. And there is a correspondence between them, right? So you can pretend really that these are all the maps from A to F. Because otherwise, then it means that our intuition is here, but formal meaning is something else, and that's bad. Okay. So that unit, I think, is just kind of complex, I know. But it is very useful. So you can use it really, both of 1 and 2. So how? Maybe in application, you see how it's gonna work. So say Yoneda is useful in computation and in definition. So let me use it somehow to show that this. So, okay, example. If let's say that C is a category, with all whatever binary product and coproduct, and also coproducts and exponentiation. Then you have this A times B plus C is always this. So we have it for sets, we know it for sets, But that's true actually for any category where you have binary products, coproduct, and exponentiation. You always have it. That's my claim. That's the theorem. So how to prove that? Of course, I have to come up with. Yes. So what is a product? So if you have two elements, say A and B, right? Then the product is one object together two morphisms, such that it is the best, meaning that if I have another C, another two morphisms, then there is a unique morphism from C to the pair such that everything commutes. And the dual of it is coproduct. Yes. And so that's it.
And the exponentiation is your single object coding all functions.
Yes, yes,
And you need it.
yes. Because that's not always true. But I'm saying that it is true. So let's say that how to prove this guy. So I'm just saying that there is some isomorphism. So you have to come up with one map such that the converse of it exists, etc. Right? And there is actually canonical map. You can see it. You can go from this to that simply because this is just plus. So it means that it is enough to go from each of these two guys to that. And then A goes to A, B goes to B plus C. But I don't want to do that because it gets something extremely big, and then you have to work with universality here and there all the time to to come up with the thing. So what I want to say is this. Instead, let's use the Yoneda embedding. Right? I have two objects. I don't want to prove that they are isomorphic. Instead, I show that the Yoneda of them are isomorphic. Meaning that, okay, so Yoneda of, so this is left, this is right, and I'm lazy. So, no. If I show this, yeah, some natural isomorphism between them, then that guy says that L and R should be isomorphic, right? Because two objects, so it is just embedding, right? It sits inside the bigger one. If in the bigger one I show that they are isomorphic, then they are isomorphic in the smaller one. We can prove it, right? Okay, why it is better to work with this? Simply because then I can apply it on X, right? And then come up with something natural in X. And so on X, it would be like this. This. And I want to show that this is nothing but home of this. I'm doing actually the wrong thing, but I have to do this right. So the best. So let's say that I go to the C opposite and I use the dual of it. Simply because the dual is meaningful here. It is enough to show that they are equal, that they are isomorphic naturally next, right? How to do this and why it is just easier? Simply because now I have two sets. Of course, parameterized with things and everything should be natural, but I have two sets. I can work with them. And I know what is the behavior of product and coproduct under this home function. Why? Because what? So I need a proof, but let's just pretend that everything is just easy. So if I start here, then since I have exponentiation, right, I can move A there and say that I have this. That's just the definition of exponential as a consequence of the definition of exponential, right? And then this guy is in correspondence with this. Why? Because if you have a map from that coproduct to something, it is just in one-to-one correspondence with one map from B, one map from C, right? So just a pair. And then these two guys, again, by using exponentiation, I can move A back. Then I have A times B, X times A times CX. And then this guy is simply that. Again, because you know what? Because plus is here, right? So I showed it. So the only thing that I have to check is that every isomorphism in between are natural in X. And they are, really. Seems, again, kind of weird. But we actually do this all the time in simpler cases. So let's say that I ask you the same thing for a poset, right? Let's say that I say that I have a Heyting algebra, simply meaning that I have a poset with binary product, coproduct, and exponentiation. And then I say that prove this. A conjunction B disjunction C is equal to this. Distributivity, right? How to prove this? There are two ways, right? So either you say that, okay, I have to show that this guy is less than this guy, and that guy is less than this guy, and therefore they are equal. Or you do the clever trick. We all know that. The clever trick is this. So instead of proving equivalence between these two, I showed this. For any x, I show that this guy is less than x if and only if the other is less than x, right? That is the usual trick. And when we do that, then we can see it. Because then I can say that B or C is less than A implies X. And therefore, B is less than A implies X. Exactly the same thing, right? So this is just a trick. Use some new X, right? But prove it for any X. This is exactly the same trick that I'm doing with morphisms. So here you have to do it for home to X because you have morphisms, not just that order. And at the same time, everything should be natural. Okay? So, yes, the point is that it is useful to have Yoneda. And then also it is useful to use, I use the first one. The second one is also useful. So to guess what we have to do in some cases. So for instance, you remember that we proved in set to the C, but equivalently in set to the C opposite, we defined two things, right? The exponentiation, the exponential functor, and then the omega one, right? To show that it is a topos. And both of them were very weird, right? The definitions. But you can come up with the definitions simply by cheating and looking into the Yoneda thing, right? So like this. So say that's easier. So I want to define omega. So what is omega? Omega, whatever it is, it should be a functor, right? Okay, and then what? And then I have to define omega of A to know what it is, right, as a functor. So this Yoneda lemma says that home of Yoneda A and F is simply f of A. Yes, I'm saying that this Yoneda lemma is helpful to define things. So there we used it for computation, right, to prove things, but it is also useful to define, to guess whatever it should be. Omega in this case. So we saw the definition before, right? But now I want to, and the definition was some kind of weird thing, right? All co-sieves, etc. But now I want to say that we are forced actually via the Yoneda lemma to pick that. But that doesn't matter really. So the only point is that it is easy to see it like this.
What properties does omega have? Or
It is sub-object classifier, so it classifies all sub-objects. So it has, yes. So the point is that I have to define omega of A, and this guy says that omega of A is in one-to-one correspondence with this guy. So then whatever it is, it should be this, because simply it's a function, right? But then now the sub-object classifier thing comes up. So I'm saying that what are the morphisms from something to omega? They are in one-to-one correspondence to sub-objects of the guy, right? So therefore, this guy should be sub of Yoneda of A, right? Whatever it is. So this is just a suggestion of the definition. It says that pick omega of A as this, and then show that it is really sub-object classifier, because there is no other way. If there is a sub-object classifier omega, you have to have this, right? It's forced upon you. The same happens for exponentiation. So you remember that we had E, F, two objects here, and then we defined, say, F to E, and it was something very weird, right? So, but now I want to say that, okay, let's define it. So I have to define it over some A. I don't know what it is, but I have to define it over A. And then Yoneda lemma simply says that it is Yoneda A, F to E, right? And then since it is exponentiation, it should have this property, right? So I'm forced to pick this as the definition. It may work, and it actually works, but I'm forced to pick this, right? No other way. So it is really helpful, simply because the definition transforms itself to the map behavior of the guy that you want to define. And the guy that you want to define is always something universal, therefore you know the behavior, so you can come up with something. Okay. So what else I have to say? So that kind of completes some part of the things that I wanted to say. Let me just remind you that you're out of chalk always. So the whole point is this. We started with a category C of some simple objects. We explained that this guy can be read as the category of generalized objects. There is one embedding Yoneda of simple to the general. And here, any F, you can capture actually all the maps into F from the simple objects as whatever is in F of A, right? So this is just a sanity check that two different interpretations of all maps in quotation are the same. So that's the whole story. Let's come back to what we had last time. Last time I asked that this is just a category of simple objects, how to construct complex objects, right? And then the suggestion was use co-limits, use gluing, right? I said that I don't like it, let's go just for this. And now I want to come back to the gluing. So the problem with the gluing was that, okay, so if you want to do co-limit or gluing of things, you have to do it somewhere. And these guys live in C, so there is nothing beyond C. If I do it here, then I end up with something simple again, which is not the one that I want, right? So how to do the thing? So now I have actually this big category. This is just the category of my generalized objects, right? If these two approaches are equivalent, then I have to have the following thing, that at least, first, it is obvious that this category is co-complete. You have all the co-limits, not just finite ones, all of them here, right? It is just enough to do the point-wise thing, right? So you have some diagram, like some very big diagram of F1, F2, whatever, blah, 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 and you want a co-limit of everything. So simply apply it on one fix A, and then everything is in set, compute it in set it as F of A, and then you see that this new F is actually the co-limit, right? So all the co-limits exist here, simply because they exist in set. But the second thing, and this is the amazing part, is that every guy here, any F here, is actually co-limit of the elements here. Or the co-limit of, do I have it? No. So what I'm saying is this. This is my set C opposite. I have some F here. The Yonedas live here, right? So what I'm saying is that this F, any F, is just the co-limit of some Yonedas inside the big one. So actually, not really, because so we know what is the diagram. So I will say that. So it is just set size things, and C is small, so there's no problem. But the thing is that actually I can construct F via gluing of the simple objects, right? I can construct any generalized space via gluing of the small spaces. And how to explain that, so I don't prove that again, because it is just lengthy. But the point is that if I claim that everything is a co-limit, so I have to come up with the description. So say F is here, and for any pick one element in F of 1A, for any A, and then the Yoneda says that this is in correspondence with what? With one map from Yoneda A to F, and let's call it X hat, right? There's a correspondence between maps from Yoneda A to F and the elements, right? So for any element, for any object A, actually I get one X hat, right? Like this. Put X hat here, right? For all the possible X's and A's, right? So could be YB and some, I don't know, Z hat. And also probably you have another YA and another X1, X2 hat, right? For two elements, right? You have one copy for any pair AX. So then you get a diagram here, and F is co-limit of that diagram, always. So you can capture actually F with, of course, all the objects and all the elements there, right? This is the whole data of F. So I'm transforming all the data to a diagram, and then I claim that I have actually co-limits here. Even more. So this is the theorem that I said that so you can say that F actually is the co-limit of that diagram. But if you like, the diagram of all the Yoneda A's for any AX in that sense, and then the canonical map here. So, but simply, I don't want to write down the whole thing. So the whole thing is that the important thing is that F is a co-limit for me now. I don't care about the canonical thing. F is a co-limit of Yoneda of A's. Right? This is the thing that I want to say.
It's like for a co-product, a generic column.
Yes, because there are maps here that I yes, of course. So there is, oh God, there is a map. So the maps are what? The maps are these things. So if you have two pairs, if you have A, X, and say B, Y, right? Then you have Yoneda of A for that there, and you have Yoneda B for that there, and then there is a map, and the map is for any map from A to B, F, there is Yoneda F here, but not for any F such that F of F maps Y to X, because it is just backward. So for any two pair, right? Any F such that F goes from A to B, but preserves the element, right? And this is the preservation of the element, and it is backward simply because F is contravariant, right? Then add one Yoneda F there.
For me, it's too complex to follow.
Yes, I see. But I don't need it really. So that's the point. So this is just to explain the situation, right?
It's where does F go?
F is in set to C opposite, right? It's an object here, or it's a functor from C opposite to set. Inside this category, actually, of some Yonedas, some elements from C. So some copies of the elements of C, because C lives here, right? Not really now, but I will say something and then we gain something, really. But at least you see something conceptual that the two different ways of coming up with new spaces from simple spaces via gluing or this looking locally, they are the same things. That's the list at least.
Okay, so so you should compare it how we got it before. So you said this is by coordinates, and then before we got it how?
Before we got it, that let's pretend that any functor is actually a space and it records all the local behavior of that weird space. This is just one way. The other way is just glue these together, and they are the same. This is the thing. So again, maybe it's good to say that in that downset things, right? You have the same situation, right? So if you have a downset D, it is always the co-limit of the principal ones. It is just the union of all downsets of A in D, right? But here you can also see that. So I have some small elements. I want some ideal elements. There are two ways. Either I come up with co-limits or with maps. So the last thing, maybe I have to go there. It's not just that everything is constructed by a co-limit. You can do it freely. That's the main point. What do I mean by that? First, formally, this is the theorem that set to C opposite is the free Cocompletion. of C. What do I mean by that? Technically, it means that there is a map, Yoneda, of course, from set to the C opposite. And for any other category D, which is co-complete, and any functor F, any, you can induce functor F hat here such that it commutes, and F hat preserves colimits. And this guy is unique up to isomorphism. Preserving colimit simply means that if you have a cone as a colimit, F of it is also a colimit cone. Yes. First, you see that it is any co-complete category. Right? The co-completion of C. Exactly. Yes. It says that first you can expand it to the co-complete category this, right? Fair enough. Then it says that it is the best one in the sense that for any other D, if you know where C goes, then you can expand it uniquely. You can expand it uniquely to all the set to the C opposite. So it simply says that everything here is constructed from colimits of C in some sort of unique way, in a free way. Right? It's similar to the cases that you have, say, one set of, say, X1.
What? Set. Is the definition of set.
That's good. The thing is the co-completeness. Every colimit exists, but the size of the thing is the set size. No, I don't have it. To see where you have your, okay, so maybe it's good to have this. So let's say that C is just the category of one object. One object, the identity. So this is just the obvious category. And then the co-completion of this, I'm claiming it is set with one, which is set, right? So let's try to co-complete this guy, right? You have just one object and you want to co-complete. At least you need what? You need all the disjoint union of this guy to itself, set size. So you get all the sets at least. Because any set is just a set union of singletons. Right? But then the point is that you get all the colimits, not just disjoint unions, but also in a free way. Okay, so I won't prove that, but the whole point is that actually you know how to construct everything here based on C in a canonical way, and then you use that canonical construction to expand it to D. So the situation is something like that. You have x1, x2, something, and then you go from this to say Z of, the free ring. If a category is a ring, then you construct a free ring or free group or whatever. And but maybe the one that's more close to our setting is just that 2 to the P thing. So let's say that I have a poset P. So I have some elements like x1, x2, and something is less than something else, etc. So then how to provide a co-completion of that? Right, because it's just a poset and it may not be co-complete. right? Maybe some unions does not exist. So you want to add them in a free way, and you can check actually this time it is not that hard, that this is of course co-complete because all the unions exist, but it is the co-completion of that, right? And free co-completion in this sense. So here I have the post-it, just use another co-complete post-it here, and then you can find the map, and that map simply maps, I don't know, any down set to F okay, let me write. So in the post-it case, this F hat simply reads a down set, say D, and it spits out this F of x's such that x is in D. What else? And then you can check that everything is fine.
I am a bit surprised or with this example of a single term and getting the category of offset. So do you really need the usual set theoretical universe with all these?
It depends. It's not something very deep. So the thing is that you want it is hidden in the definition of co-complete. What is co-complete? It means that for any set, if I have a set size diagram, then the co-limit should exist.
The set size, it has a structure of the set somehow?
No. So you have a set of elements and morphisms, not a class. That's it.
So if you, in other words, if you want to show that this category that you get, the free co-completion contains a particular set, then you take this set and you take a category describing this set, and then you get and take the limit with respect to this category.
Yes. So you need some set theory to define co-completion, and this is that one. No, it's not deep. So you get exactly what you had before. So
Not saying that I see it completely true, but now I believe.
yes. Okay. So what? So it's the free one, and this is just the propositional version of it. So I have just 5 minutes, and I can show you the glimpse of the two problems at least, or not. Oh God. Next or next of next. So the thing is that we are extremely slow. So I'm fine. But it seems Neil is not fine. So the point is that we are somehow in the middle. So I have to define other set theoretical. So I have to finish this, right? The problems here, and then I have to solve these problems. Therefore, I need some sort of generalization of set to the C opposite, and then we see sheaves, which is just a generalization, and then we see Boolean valued models, but not in an extensive way, just description, etc. And then we have to see the realizability thing as well. And then we have to move to, so now we have all the toposes that we need. Then we can go and then investigate abstractly what is the connection between logic really and toposes. That the thing that I just claimed that you can always interpret intuitionistic logic inside the topos, right? And so now everything is complete. So we can use some of these constructions depending on the case, to prove some independence results from some theories, including ZFC. Yes.
You say this, I kind of lost count. You're saying this is about lecture 8 already?
Yes.
Okay, so another.
Huh?
Another.
Maybe.
Okay.
But with this pace, maybe even more.
And it's all going to look kind of like this.
Yes. I'm afraid yes. So no, the thing is, I'm trying hard really to avoid the real categorical thing, and it is just a glimpse of it. I can do that, but at some point we have to just observe it, right? Because otherwise, but we can, I don't know, do something about it. So,
Well, at this point, I'm just asking for information, so we know where we are. So, okay.
okay, so that's fine. But at the same time, if you okay, let me go with this proposal. Because I'm not in no rush, right? So we can just there is, as Pavel said, there is no need to do it just in one semester or what. However, the only thing that I'm caring is that I do not lose you in the middle of just two complex things, right? So if you feel in some sense that, okay, it is just too complex now and with no examples whatever, right? So we can just stop for one session or two or whatever, and then just answer all the questions and solve some examples, open up things for anyone who wants to see, you know, the details if it helps, or just in any way it helps, I don't know. It takes time to observe the language really, and seeing more examples and doing things with hand, right? It helps. Or anything that you can come up with as some sort of, if it helps, just say.
I think it would help very much if you sometimes write down definition and so on, and then observation or fact. Just write it explicitly, because then we will have certain fixed forms where we will be able to actually ask questions. So you want to do it very informally, but it is good to have certain particular
I see.
questions where one can say, okay, at this point, I don't understand. I can ask this question.
I do like actually to do that, but the problem is that it is just too heavy, and I have to. So going informal is my attempt to, sweeping things under the rug. Because if you write down everything or some definitions even in more detail. Sure. Thanks. Anything?
Yes.
That was very firm, yes. Okay. Sure.
Just wanted to ask, so is 2 to the p less than or equal to
Yeah.
all? That's this isomorphic to the category set to the
It's analogic to that, yes.
analogic, or but
It's-
this says this theorem works for any category, right? So I can just put there the both sides.
That's true. Yes. There is a subtle difference. So the thing is that, how to explain? Being free co-complete is a relative thing, right? Meaning that what you pick actually as families here, right? So you say that it is free co-completion, meaning that it is co-complete, and with respect to all co-complete categories, you have that. This is also free co-completion, but not with respect to all co-complete categories, but all co-complete posets. So it's different version of free.
Because the categories I'm testing are small.
Because they are small, yes.
Poset is small.
Poset is small, yes. But it's not just that, it is a poset as well. It's not it's not any category, it's just poset. I'm restricting my things.
There exists a small category
Yeah.
such that if there is the C is the poset, the set C of is the 2 to the poset of, and D is the small category that such that that morphism does not exist or is not unique?
What you explain is actually that you have to choose D as a complete poset, right?
Oh, no, my question is, so I first thought that this works because we're talking about like small categories. But not.
Not just that. Also the fact that we are talking about posets. Right? We restrict the domain of the discourse to just posets and say everything else. Okay, so next time, now I have two descriptions, right, of one thing, all the pre-sheaves as generalized spaces, as functors actually, and at the same time as the result of gluing things together, right, the simple things, in a very free way. So next time I want to say that what I don't like about these two pictures, one then would be the geometric problem that I have. The other is the algebraic one. So I have to use these two pictures to say that why it's not generalized enough.
Right, can you say what the two pictures are again? So I think you said that the set to the C of, you call that the constellation,
Yes.
and then what's this glue?
So the gluing thing is just this free co-completion or co-completion thing, right? It says that any object here is a co-limit of the objects from C. Therefore, any complex object is just the result of gluing of simple objects, right?
And we should see this as a different way of viewing the subject.
Yes. Yes. Or the whole category, right? So you can read this as just say Z of x1 up to xn, the free ring as opposed to the C, right?
Okay, and you'll say what the problem is, and you said the thing you've written up there, I've no machinery to produce fully on top of it. That was the logical problem.
Yes.
Okay.
Okay.